Hello class. We're going to start off our discussion today about the physical properties of alcohols. And a really good way to do that is to compare the physical properties of alcohols to alkanes and alkyl halides. So if we take a look and we draw a Lewis structure here of ethane, all right, I want to highlight this hydrogen in pink. So there's our ethane. And then let's draw ourselves chloroethane. Drawing ourselves a chlorine right here, carbon-chlorine bond. And then we will compare that to ethanol. Now what's interesting here, or something that we need to understand, is we're trying our best to compare apples to apples. And the way that we're doing that is, yes, the pink atoms here are different, but the green parts are the same. So when we compare the, let's say, the boiling point of ethane to ethanol, what we're trying to do in order to say, hey, when we take a look at the differences of their physical properties, the green part has to be relatively the same in order for us to make a comparison. So what I'm saying, what I'm trying to get at is, let's say it would be not a good idea to make a comparison of ethane to this alcohol down here because it has so many more carbons than ethane. A better comparison would be ethane to ethanol. And when we take a look at the boiling points of these three molecules, we're not going to worry about this one. We'll see that ethane has a boiling point of negative 89 degrees C. Chloroethane is 12 degrees C. And the boiling point of ethanol is 78 degrees C. So what's happening here? Really, really, really low boiling point, high boiling point. Why is this trend like this? It all has to come, it comes down to what the alcohol can do that these two cannot do. And that is hydrogen bonding. Recall from general chemistry, what is a hydrogen bond? It is simply a bond, and we'll call that X. X, let's write it down here. X can be oxygen, nitrogen, or fluorine. Those are the only ones that can be used in hydrogen bonding. So for example, if we had water, we would have a bent molecule. We'd have some lone pairs here. What can happen is this hydrogen right here can hydrogen bond with another water molecule like this. And I'm going to cut off that hydrogen. So let's redraw this. So what if we had water like this? Okay. And then we had another water molecule oriented kind of like this. Like so. If you have a hydrogen that's directly attached to a oxygen, nitrogen, or fluorine, you can generate a hydrogen bond right there. And why can we generate this hydrogen bond? Because remember, the oxygen is more electronegative than hydrogen. So what it's going to do is it's going to generate a partial negative on the oxygen and a partial positive on the hydrogen. And so when this water molecule gets close to another water molecule, we have a partial negative on that oxygen and a partial positives on these hydrogens right there. So what we have here is a interaction between a partially positive and a partially negative charge. And so that's represented by that dotted line right there. And that the green dots right there, that is the hydrogen bond. So that is the hydrogen bond there. And these guys don't have any hydrogen bonds because they don't have any hydrogen atoms directly bonded to oxygen, nitrogen, or fluorine. And that is the reason why you have such a drastic difference from ethane all the way to ethanol. It's because of that hydrogen bond. Very, very important in chemistry, in biochemistry. This hydrogen bond is responsible for a lot of physical properties that you're going to see throughout your chemistry career. Now, the hydrogen bond is going to help us explain these physical properties of miscibility and solubility. Now, these words may sound like they are describing the same thing, but in fact they're not. So let's take a look at methanol. What is methanol? Sometimes you'll see it written like this, methanol, or sometimes you'll see it like this. Right. Now, methanol is going to be miscible with water. So that means you can take methanol and add it to any amount of water, and it's going to mix perfectly. So let's contrast that to if you have water and oil. You put them together, what happens? They're immiscible because you're going to have the oil layer and the water layer. And typically when we talk about the water layer, we call that the aqueous layer. So you're going to have the oil layer and the aqueous layer, and they don't mix. They're not miscible. But if you took 1 part methanol and 1 part water and mixed them together, 100% miscible. If you took 100 parts methanol and 1 part water, 100% miscible. Perfect. They just mix. There's no layers. And if we do the other way, in whatever ratio that you add methanol to water, it's going to be 100% miscible. And the same thing for ethanol. All right. But then, let's talk about why methanol is perfectly miscible in water. It's because of the hydrogen bonding here. Because you look at methanol, and I'm going to represent it like this. Okay. Do you see how in methanol we have a hydrogen directly attached to an oxygen atom? So that's really cool because now when you have water floating around, when you put methanol into water, what can you have happen? That's not the best way to actually draw it, because you'll learn that the best hydrogen bond is when they're head to head, drawn like this. Okay. So that angle between this oxygen, this hydrogen, this oxygen is all in a straight line. That's the best way to get the strongest hydrogen bond. And so that's what we have right here. So methanol can hydrogen bond very well with the water, and that's going to make it miscible because of that strong hydrogen bond. And the same thing for ethanol, a lot of hydrogen bonds there. In contrast, if you say we take butanol, and butanol has 4 carbons. Let's double check, 1, 2, 3, 4 carbons. So butanol is not miscible in water. And what that means, but butanol is soluble in water. Like, what am I trying to say here, okay? Well, when we talk about solubility with regards to butanol, only a certain amount of butanol is soluble in water, can dissolve in water. So you reach a point where if you have a, let's say, a beaker of water here. Okay, we have a beaker of water, and you put in a drop of butanol into the water, it's going to be soluble. But if you start adding more and more and more butanol, it won't be soluble anymore. And the reason is because when you take a look at butanol, and when you take a look at methanol, let's look at the different properties of, or different parts of the molecule. So when we take a look at methanol, what do we have? We have a CH3 part and a OH part. So that's methanol. Compare that to butanol, 2, 3, 4, 5. Look at this. What we have is two regions. We have a region that is just made up of carbon and hydrogen, and that is called a hydrophobic. A hydrophobic region. Now, hydro meaning water, phobic meaning fear. This hydrophobic region is scared of water because it is very, very greasy. And grease and oil and water don't mix. We've learned this. But why is methanol miscible in water? Because it has another part. It has this part right there, which is hydrophilic. We have a hydrophilic part of the molecule, which is water-loving. So this loves to interact with water via a hydrogen bond. And so we have a greasy part and a water-loving part, or said another way, a hydrophobic part and a hydrophilic part. The hydrophobic part is relatively small in comparison to butanol. So if we take a look at butanol, we have this piece right there, which is obviously much larger than one carbon. That is still the hydrophobic. And this is still the hydrophilic. So we have both parts on both molecules. But because on methanol, this hydrophobic region is small, the hydrophilic part can overcompensate and interact with water and make it 100% miscible. Whereas in butanol, the carbon chain is getting larger. It's getting more greasy. So it's going to make it more difficult for water to interact with this part of the molecule and make it miscible. So that is why butanol is considered soluble in water up to a certain point. You can add a little bit of butanol to water and it will dissolve. But if you add too much, then these hydrophobic tails or these hydrophobic carbon chains are going to start interacting with one another and make it insoluble. And then if you extend this concept out to, let's say, octanol, so 2, 3, 4, 5, 6, 7, 8. Now we have a really, really big hydrophobic piece, okay, and a small hydrophilic piece. This is just so large, and it's just going to make this butanol insoluble in water. So there's a size dependence of how large this hydrophobic piece can be, and depending on how large it is, determines if it's going to be miscible, soluble, or in this case, insoluble. So depending on the textbook that you are going to read, there's different ideas out there. But one idea is that if you have 8 carbons in the hydrophobic region, and you have 1 alcohol or 1 hydroxyl, we also call these hydroxyl groups. So the OH is a hydroxyl. So you have 8 carbons, 1 hydroxyl, that's going to be insoluble. If you have less than 8 and a hydroxyl, then it's going to be soluble, but how soluble? There's going to be a range there. Methanol and ethanol are going to be miscible because their hydrophobic piece is relatively small. Interesting and fun physical properties. And it comes down to hydrogen bonding and how it interacts with water, and the hydrophobic and the hydrophilic parts. So let's take a look at the pKa of alkanes, and let's take a look at the pKa of amines and alcohols and some halogens here, like this. Now, what are the pKa's? Alkanes are what? Approximately about 50, 45 to 50. Amides are around 35 to 40. Alcohols are what? 15 to 18. And then -10 to 3. Okay. So that doesn't look very well. So what I'm saying is we have -10. So that's hydroiodic acid, HI. And then when we go all the way up to hydrofluoric acid, so that's -10, that's approximately 3. Now we can say we have these numbers to help us understand the acidity, but what if we didn't understand or didn't know these pKa values? Then we can qualitatively look at it based off of the stability of their conjugate bases. So we could take a look at these, and when the hydrogens are ripped off, we would get these negatively charged species, like so. And so is an alcohol more acidic than a amine? Well, look at its conjugate base, and you can tell the acidity when you're comparing 2 molecules by looking at the stability of their conjugate bases. So you can see a negative charge on a nitrogen atom is going to be not as comfortable as a negative charge on an oxygen, because oxygen is more electronegative. It can tolerate that negative charge better than a more or a less electronegative nitrogen atom. And we've learned those principles before in our acid-base chapters. But I want to remind you of that. Now, when we go from an alcohol to this negatively charged species, we call that an alkoxide. So we have these alkoxides. And alkoxides are an important part in organic chemistry, because look at this alkoxide now. You can see that it is electron rich. So that electron rich species can behave as a nucleophile or a base. So we want to form alkoxides to do a reaction. So it begs the question, how do we make alkoxides? Well, you have to choose a correct base to do that. And a really good base to rip off this hydrogen and generate an alkoxide is sodium hydride. Sodium hydride there. So you can envision sodium hydride simply looking like this. Not a nitrogen. It's kind of how we can envision this reagent here. And when you have hydrogen with a negatively charged, or with a negative charge, we call that a hydride. And so this hydride mechanistically can come in. Let's make sure we have that oxygen-hydrogen bond there. The electrons on that hydride can come and abstract that proton, break the oxygen-hydrogen bond, and give us this, and give us our alkoxide. And then look what it makes. It makes hydrogen gas. And so that hydrogen gas is going to bubble away from the reaction. And Le Chatelier's principle says, okay, we're losing this. So we need to force this reaction to go to products. So that is one way to form our alkoxide, is treating it with sodium hydride. The second way that you could do this is adding the alcohol to a metal. Not just any metal, but it could be, so let's draw ourselves our generic alcohol. And if we treat that with lithium or sodium or potassium, you can generate your alkoxide. Now, why is this reaction? What's also happening? Yes, you're generating the alkoxide, but it's these metals that are facilitating the generation of hydrogen gas. You don't need to know mechanistically how that's happening. Just remember that when you add lithium, sodium, or potassium to alcohols, you generate your alkoxide and you liberate hydrogen gas. So those are two common ways for you to make alkoxides. Let's continue our discussion on the factors that affect the acidity of alcohols. Now, we've covered and talked about all these principles before, but I see no harm in reviewing it because it's so important. So if we take cyclohexanol right there versus phenol, which one would you predict to be more acidic? Let's say we don't know our pKa values. Which one would you think is the most acidic? Well, remember, qualitatively, the best way to do that is to look at its conjugate base and look at the relative stabilities. All right, so this would be the conjugate base, and this would be the conjugate base. Like that. So if we go through the cardinal rule, we would be like, okay, the cardinal rule says take a look at charge. They're the same charges. Let's see, A stands for atom. They're both oxygens. So if we write it down here, cardinal rule. So R, resonance. So charge, atom, resonance. Look at does this have a resonance structure? No, it doesn't. Does this have a resonance structure? Yes, it does. Look, we could bring in a lone pair here and then take those pi electrons and stick it on that carbon right there. And so we would get a a resonance structure that looks like this. And so just based off of doing your cardinal rule, you'd be like, oh, the phenol right here is going to be the most acidic. And when you compare the pKa's, pKa of this guy is, let's see, 18. And the phenol has a pKa of 10. That is significant. It's not 18 minus 10 is 8. This isn't 8 times more acidic. It is 10 raised to the 8 times more acidic. And why? Resonance. So that's another key factor that affects acidity of alcohols, resonance structures. What's another one? I stands for induction. So we could have some examples here of alcohols that are more acidic based off of that. Oh, before I go, this negatively charged, the alkoxide version of phenol has a special name, and we can call that phenoxide. Okay, so let's get back to what that structure looked like so we're all on the same page here. So that's like that is the alkoxide from phenol, but phenol, or the alkoxide from phenol has its name phenoxide. But I'm not too picky about that. So let's take a look at another alcohol and see how the acidity changes. So let's take a look at ethanol versus trichloroethanol. So trichloroethanol. So 1, 2, okay. Qualitatively, which one would you think is the most acidic? Well, you would have to take a look at the conjugate bases. So if we go through the cardinal rule here, charges are the same atoms. There's no resonance, no delocalization. Induction effect. And we can see that we have some very electronegative atoms on the trichloroethanol, or ethoxide piece. And so what's that going to do? It's going to pull electron density towards itself. And so it's going to pull the electrons through the bonds. So this negative charge over here is going to feel a pull in this direction towards those more electronegative atoms. And that has a stabilizing effect, because when you take a look at this one, the ethoxide, what's going on here? This negative charge here is localized. It is staying on that oxygen. It does not go through the bonds because there's nothing on these atoms right here that's pulling electron density. There's no electronegative atoms. So that is not happening. But in contrast, when you have the chlorine atoms here, it is pulling electron density. And that effect is called induction. And so this conjugate base is going to be more stable than this conjugate base because this one has induction. And we can see that the answer here, this has a pKa of approximately 16, and this has a pKa of about 12.2. So we can see, based off the numbers, this one is more acidic. But when you don't have numbers, you have to look at it through the lens of this cardinal rule thing. Okay? So that's another factor that affects the acidity of alcohols. Now another factor that isn't included in this acronym right here is solvation effects. So let's write that down here. So solvation effects can be, we can talk about that by looking at ethanol versus terbutanol. Okay, so there's terbutanol. Now with the pKa's, this ethanol we said was already 16, we saw that before, and then terbutanol is 18. So which one is more acidic? Well, it's the one with the smaller pKa. So ethanol in this case is more acidic. We do the same concept here where we have to look at the conjugate base. Now when we take a look at that conjugate base of these two, we'll go through the cardinal rule and we won't see anything that's going to break the tie. Like, how do I know this conjugate base is more stable than this conjugate base? Just by looking at the cardinal rule. We don't have anything there. It's the solvation effects. And so what that is when it's a steric argument. When you have less sterics, you can have more solvent molecules solvate that anion right there. Now these X's, green X's, I'm just representing those as solvent molecules, that they can solvate that anion very well. But when you have this steric bulk here, it's going to make it more difficult for solvent to encapsulate or solvate this anion. Now, who cares? Why do we care about solvation effects? What is it doing? Well, this is a negative charge, which is high in energy, right? When you have solvent molecules interacting with that negative charge, it helps to stabilize it. It helps it out. So if you can put more solvent around this alkoxide here to stabilize it, in comparison to the terbutoxide here, you can see that there's going to be less solvent around due to the sterics here. Now, that's not drawn where you can see it very well. But if you take a look at your textbook, you're going to see a space filling model, which illustrates that better in a visual context. But the principles that I'm teaching you, you can see that there's 4 X's over here, which represent solvent, and I only have 2 over here. So there's less solvent solvating this anion, which doesn't stabilize it as well as this one. Okay, so solvation effects. Make sure you understand that. Okay. Now let's talk about how to prepare alcohols. How can we make them? And this is going to be a review. The first way to do it is a substitution reaction. Recall that if you have a primary alkyl halide and you treat it with a strong nucleophile, such as sodium hydroxide, you can do a SN2 mechanism and generate a primary alcohol like so. Or if you had a tertiary alkyl halide like so, you could treat it with a weak nucleophile such as water, and you could get your tertiary alcohol like so. And that would undergo by a SN1 mechanism. You could also look at, let's see, addition reactions. So addition reactions would look like where you would have a alkene. And if you treated the alkene with dilute sulfuric acid in some water, you would generate a secondary alcohol like so, like that. What are some other addition reactions that we have learned that could give us a alcohol? What about the oxymercuration reaction? And that is done in 2 steps, where you take the mercury diacetate here piece, and you have that in some water, and then you do step 2, and it might get blocked off. Let's see here. Yeah, you can't see that. So let's write step 2 would have to be the reduction. So step 2, let's put it up here. I know that's a little unorthodox here, but that's when you treat it with sodium borohydride. And that would generate ourselves the same product. So that reaction is oxymercuration reduction to give us our secondary alcohol. What's another reaction that we've learned to give us alcohols? What about the hydroboration oxidation reaction? Remember that one? And that is also done in 2 steps. So you have to do the boration part, which you take your borane in THF, and then you have the oxidation step. So you have to add your peroxide, H2O2, and some base. All right. Now, under these conditions, do we generate our secondary alcohol? No, because the alcohol is going to go to the least substituted carbon. We'll go right there. So that, all those reactions are reviews. So what we're going to do now is introduce more ways to make alcohols. And that is through a process called reduction. So reductions. Okay. And overall, what reductions do is that it's going to take a carbonyl compound, so a ketone, for example, and it's going to do a reduction reaction. I'm not going to show you what those reagents are yet. And it's going to turn it into a alcohol. So isn't that cool? So let's just, in our mind, or you write this down in your notebook, how can you make alcohols? From alkyl halides and from alkenes. So doing substitution reactions, addition reactions, and now a third way, reductions. So in order to understand what's going on in a reduction, we need to understand and review oxidation numbers. So in order to understand oxidation states, let's do a compare and contrast here with the molecule methanol. All right. Now we can understand that we could represent this representation like so, right? Because those covalent bonds are because there's electrons. So here's methanol, here's methanol. These are all covalent bonds. Now, when we want to calculate the formal charge of this carbon, what do? Well, we treat the molecule as if it's all covalent. And we go to the periodic table and say, okay, how many valence electrons does carbon have? And we said, hey, it has 4. And then we minus how many electrons the carbon owns. So we come over here and say, okay, well, they're sharing these 8 electrons. So it technically only owns half of those. So we would say, okay, it only owns those 4 because it's sharing the other 2. So 4 minus 4 equals 0. So that carbon atom would have a formal charge of 0. But when we want to look at oxidation numbers, it does it a little bit differently. It's now going to look at methanol as if it were ionic. So when you look at all these lone pair or these electrons here, now we're going to look at it through the lens that, hey, we're going to envision this as an ionic species. And we're going to take all these electrons and give them to the atom that is more electronegative. Okay? So when we take a look between this hydrogen and this carbon, which one's more electronegative? The carbon is. So we're going to put all the electrons around the carbon. So we do that for this carbon hydrogen. And we can see carbon's going to win again. And this is going to win again, like so, like that. But which one's more electronegative, oxygen or carbon? Oxygen is. So oxygen's going to win this time. Okay? And then we are going to put a box around how many electrons that carbon owns. So what is the oxidation number for carbon now? And the way that you do that is you take how many valence electrons it has, supposed to have, and then count how many electrons it owns. 1, 2, 3, 4, 5, 6. So that equals a -2. This carbon has an oxidation number of -2, but a formal charge of 0. They're just two different techniques for counting electrons. So if we continue this exercise to figure out the oxidation number for every atom in methanol, what would we do? Well, these lone pairs on the oxygen atom are still there. Okay? So let's do the oxidation number for oxygen here. That would be 6 minus what? Oh, wait, we still have to do this one. So that hydrogen, this bond right there between the oxygen and hydrogen, oxygen's more electronegative than hydrogen, so we would have to put that lone pair there. So what's the oxidation number for this oxygen? How many valence electrons minus how many electrons it owns? 1, 2, 3, 4, 5, 6, 7, 8. So that equals a -2. And then what's the oxidation state of the hydrogens? Well, hydrogen has 1 valence electron minus 0 electrons around it equals a +1. So the hydrogens have a +1 oxidation number right there. Now, when you take a look at all the oxidation numbers here, they have to sum up to the charge of the molecule. And the charge on the molecule is what? Neutral. So we see that there's a -2, a -2, so now we're at -4, but then we have 4 positives. So that all summed up equals 0. Okay, so that's how you do oxidation states. Now, using this method right here of calculating oxidation numbers will help us to figure out if a molecule, when it undergoes a reaction, if it's been oxidized or reduced. So let's demonstrate that. Let's say we take methanol and we do a lot of reactions and we convert it into formic acid. It looks like this. Okay. Now, we've already established that the oxidation number for this carbon in methanol is what? A -2. So now, when we went from methanol to formic acid, what has happened? Did we do an oxidation or a reduction? And to figure that out, we have to figure out now the oxidation number for this carbon. So we do it the same way that we did it before. So hydrogen, carbon, which one's more electronegative? The carbon. So it gets the electrons. Carbon, oxygen. the oxygen. Carbon-oxygen, oh, we have double bonds here. Remember, though, there's still the lone pair there. But we're talking about these electrons between the carbon and oxygen, and clearly, oxygen is more electronegative. So now we just put a square around the carbon. How many valence electrons does it have? 4 minus how many electrons does it own? 2 equals 2. So this carbon now has a new oxidation number of +2. So what has happened? Just by looking at the numbers of before and after, when the oxidation number increases, so we went from -2 to +2, it has increased. And so when the oxidation number increases, that equals oxidation. So we could look at this in the reverse as well. What if we started with formic acid and converted it to methanol? We would be like, okay, it started at +2, went to -2, so it has decreased in oxidation number. So when the oxidation numbers decrease or get smaller, we have reduction. All right. So let's take a look at just one other example that you might, another situation that you might encounter. And that is when you have other carbons attached. So let's take a look at a ketone like this. How would you calculate the oxidation number for that carbon? Well, we would do our analysis like we always have, like so. Now, the carbon-oxygen is easy. We know oxygen is going to be more electronegative, right? So we're going to put the electrons on that one. But now when you have two atoms that are the same electronegativity, which one gets it? Well, in that situation, they both get 1. So this one stays with that guy. So I'm just getting it more closer. And so now when we calculate the formal or the oxidation number, that's what we count. So that would be what? 4 valence electrons minus how many it has. So that would be a +2. So that's an oxidation number of +2. Okay. Another way that you can look at a reaction or a transformation and know if it is an oxidation or reduction, and you don't want to use these numbers, you can just simply look at the before and after. Okay. So in this particular case, before, after. If you add more bonds to oxygen, look, 1 oxygen atom, 2 oxygen atoms. When you do that, that is an oxidation. A reduction is in the reverse. If you start with the formic acid and go to the methanol, what have you done? You have reduced the amount of carbon bonds, you have reduced the amount of carbon-oxygen bonds and replaced them with hydrogens. So if you're adding carbon-hydrogen bonds, it's undergoing a reduction. Or more broadly, if you're adding hydrogens to the molecule, it's a reduction. Okay? So if you take a look at this example right here, without calculating the oxidation numbers, What has happened? A reduction or an oxidation? Well, you can see that you have more oxygen atoms, so that's an oxidation. So what if you had a ketone like this and you turned it into an alcohol? What has happened? You've done a reduction. Why? Because you've added a hydrogen there, you've added a hydrogen there. That's a reduction. So that's a quick and easy way to know. But also understand that you should be able to calculate the oxidation numbers as well.